So we will now study approximation by smooth functions. So we have already seen one result of this kind, namely if you are in W1P of Rn, you can approximate it in that norm by means of functions which are in W1P D of Rn. Okay, so we want to know to what extent this will carry out in other open sets. So we first start with a technical lemma. So omega in Rn be an open set, and you let u be a function from omega to r. Then let u tilde be its extension by 0. So what do you mean by that? So this notation we will use all the time. So u tilde of x will be equal to u of x if x is in omega, and 0 if x is in omega complement. So you just take the function blindly, extend it by 0. So if u belongs to W1P of omega and psi belongs to D of omega, then psi u tilde. So you multiply u by psi. So you multiplying by C infinity function with compact support. Now you extend it by 0. This happens to be in W1P of Rn. And for all 1 less than equal to I less than equal to n, you have the formula for the derivatives d by dxi of psi u tilde equals psi du by dxi plus d psi by dxi times u, the usual product formula applied tilde. Okay, so this is the formula. So proof. So if u is in LP of omega, this always implies that u tilde is in LP of Rn. In fact, the norm will be the same, in fact. So the norm, even the norm won't change. So you have that this is true. So in view of the statement, so if psi u is in D of psi is in D of Rn and D of omega, and u is in W1P of omega, so the product will be in LP of omega. So its extension by 0 is in LP of Rn. So if I can prove this formula for derivatives, since all this inside the bracket is still in LP of omega, so the tilde will be in LP of Rn, and therefore the derivatives are in LP of Rn and the function is in LP of Rn, and that will prove that psi u tilde is in W1P of Rn. So enough to show star. So it's enough to prove the formula for the derivatives. So that we straight away calculate. So let phi belong to D of Rn. So what is integral over Rn? Psi u tilde d phi by dxi dx. Okay. Now that is equal to integral on omega psi u d phi by dx. So let me now write this is equal to integral omega u into psi d phi by dx. I will write as d by dxi of psi phi minus phi d psi by dxi dx. Okay, so this is just the product rule for two smooth functions, and then I have just used it. So now if I write this is equal to minus of, now psi phi belongs to D of Rn, D of omega, sorry, and so I have u times the derivative of a d omega function. So that is nothing but integral on omega, by definition du by dxi acting on psi phi. Okay, and then minus of u deep psi by let me write it different, deep psi by dxi, oh no sorry, u deep psi by dxi into phi, okay, dx. Okay. And that's equal to integral over Rn with a minus sign of psi du by dxi plus deep psi by dxi u tilde phi dx, and that proves the fact. Therefore, the derivative. So this implies this implies star. Okay, so that immediately you have the theorem. So this is just a very simple lemma. So now we have the theorem of Friedrichs. Okay, let 1 less than equal to p strictly less than infinity. Omega in Rn open set and u in W1p of omega. Then there exists a sequence un in D of Rn such that un converges to u in Lp of omega and dun by dxi converges to du by dxi in Lp of omega prime for every omega prime relatively compact in omega. So that means, so omega prime, what does this mean? Omega prime relatively compact in omega. That's the notation, which means that is omega prime closure is contained in omega and omega prime closure is compact. Okay. So in the case omega equal to Rn, we had u in d, un in d of Rn such that un converges to u in Lp Rn and dun by dxi converges to du by dxi in Lp of Rn. Now here because we are in an open set in the domain and not in the entire set, we have to pay a price for it, and that is we lose the convergence of the derivatives in the entire set domain, but we can do it in any relatively compact subset of it. So that is the what this theorem is telling us. So let us try to prove this. So as before, we will always denote by tilde the extension by the, so rho epsilon modifiers, and we know that rho epsilon star u tilde converges to u tilde in Lp of Rn. Okay, so we all know this. So now let omega prime be relatively compact in omega. Remember, this is the definition of relative compactness. Okay, so then we can find omega double prime open relatively compact in omega such that omega prime is relatively compact in omega double prime, which is relatively compact in omega. So let us assume, so you have omega is here and this is omega prime. So I can put one more relatively compact set omega double prime inside. So that is what this question of Rn and its topology. You know, we have T3, T4 spaces and all that. This comes from those properties. Okay. So now let psi belong to d omega such that psi is identically 1 on omega double prime, and you take d to be the distance from d omega prime to d omega double prime. So it is the distance between these two boundaries, the smallest distance which you have between the sets there. Okay. So now what about, so this will be strictly positive because you have two disjoint compact sets and consequently the distance is positive. Okay. Now support of rho epsilon star psi u tilde minus rho epsilon star u tilde this is equal to support of rho epsilon star psi tilde minus 1 u tilde. Yes, just I have taken out the common factor, and now support of a convolution that will be contained in B0 epsilon closed ball with radius epsilon and plus support of 1 minus psi tilde, and that is the same as the support of 1 minus psi, because psi tilde, psi is a function which is C infinity with compact support in omega, and outside omega I only have extended by 0, so I have really not done anything to it. So 1 minus psi. Okay. Now support of 1 minus psi is somewhere here, because on omega double prime psi is equal to 1, and therefore the support of omega double prime will be contained, support of 1 minus psi will be outside 1 minus double prime, and to that you are adding a epsilon distance, ball of radius epsilon. So you will have to include a small portion here. Okay. So this will be contained in Rn minus omega prime if epsilon is less than d. So as long as I don't add something more than the distance between these two boundaries, so the small thin layer which I am adding is going to be well near the other boundary, outer boundary, and therefore this will be contained in omega prime. So support of these two functions lies in Rn minus omega prime. So on omega prime we have rho epsilon star psi u tilde is the same as rho epsilon star u tilde. Now rho epsilon star psi u tilde belongs to W1p of Rn, and what about its derivatives? D by dxi of rho epsilon star psi u tilde equal to rho epsilon star d by dxi of psi u tilde, which we have computed, which is rho epsilon star d psi by dxi of u plus psi du by dxi, and this converges in LP of Rn. So what will this converge to? This will converge to rho epsilon star something is going to converge to the same, whatever it is. Okay, so that will converge to d psi by dxi u plus psi du by dxi tilde. So in particular, restricting to omega prime, we have d by dxi of rho epsilon star psi u tilde equals which we know is equal to d by dxi of rho epsilon star u tilde, because we have this condition here. Rho epsilon psi u tilde is rho epsilon star u tilde. So, d by dxi rho epsilon star u tilde is in omega prime. So, restricting to omega prime is important, equal to this. And if you use the properties of psi, what is psi is identically 1 in omega double prime. So, in particular omega prime. So, d psi by dxi is 0 and psi is identically 1, and that is just equal to du by dxi. Okay. So, now you choose epsilon k to be a sequence of real numbers going to 0, and then you take Vk equals rho epsilon k star u tilde. Then what do you know? We know that Vk belongs to C infinity of Rn, Vk converges to u in Lp of omega, and for all 1 less than equal to I less than equal to n, dvk by dxi converges to du by dxi in Lp of omega prime for all omega prime relatively compact in omega. So, now we have got our C infinity functions. From C infinity functions to go to C infinity functions with compact support, that is exactly the theorem which we have done already once. So, we do not have to repeat that technique. So, all we have to do is let zeta belong to d of Rn, support of zeta contained in B02 and zeta identically 1 on B01, and you take zeta k equals zeta of x over k exactly as before, and then you take uk equal to zeta k vk. This will belong to d of Rn and has all the required properties. This is just a repetition of the previous theorem's proof, because once you have proved something which is this, then multiplication by zeta k will produce exactly the same properties, and therefore you have nothing else to do. Okay, so we can approximate u by d of Rn function in Lp, but if you want to approximate the derivatives, then you have to pay a little price. You can only do in relatively compact subsets. So, the question you ask is, can I ever do in the whole space without losing on omega? And that you can do provided you have what is called an extension operator. So, we have definition. So, omega in Rn open set, a bounded linear operator P from W1P of omega to W1P of Rn is called an extension operator I already mentioned this yesterday. So, P u restricted to omega equals u for every u in WMP 1P of omega. So, this is the notion of a extension operator. Okay, so you note that you have norm Pu of 1 P Rn is less than or equal to some C times norm u of 1P omega for all u in W1P omega. This is the condition that it is a bounded linear operator. Okay. So, now the theorem says, if there exists an extension operator on WMP 1p omega, then given u in W1p omega, there exists un in d of omega, Rn sorry, such that un goes to u in Lp omega and dun by dxi goes to du by dxi in Lp omega. Now you do not have to worry about relatively compact sets for all 1 less than equal to I less than equal to n. Okay. So, again all this results is for 1 less than equal to p strictly less than infinity. Okay. So, proof is just one line. So, if p is the extension operator, then there exists un in d of Rn such that un goes to pu and dun by dxi goes to d by dxi of pu 1 less than equal to I less than equal to n in Lp of omega, Lp of Rn. So, now you just take un, so this un itself will work. Therefore, so since pu equals u in omega, result follows. So, the question is when do we have extension operators? We will see that it depends on the nature of the set omega, in particular on the nature of its boundary, and therefore how we can extend depends on the domain. Okay, and we will see results which talk about that. Okay. Now, what does this theorem mean? It means that if you have u in W1p of omega, so remark, this is small p and there exists capital P extension operator, then u can be approximated in W1p omega by restrictions of d of Rn functions, which are C infinity functions in particular in omega. So, we have a more difficult theorem called the Mayer's-Serrin theorems. You can find a proof in Adams, the book which I cited. Okay, CF Adams. Mayer's-Serrin theorem says C infinity of omega intersection W1p omega is dense in W1p omega 1 less than equal to p less than infinity. Okay, so if you have a C infinity function which is dense in which is also a W1p omega, see, because if omega is unbounded, you cannot really say that a C infinity function is an LP. Okay, so you have to put this intersection. So it should be a C infinity function and it should also be such that it's in W1p omega. Such functions may or may not be restrictions of d of Rn functions. Okay, so that it says that if you have such C infinity functions which are in LP, they are also dense, so you can approximate it by those functions. Okay, fine. Okay, now final remark. No such results for p equals infinity. You don't have any approximation result. For instance, if you take W1 infinity of Rn, you have u identically 1, u is in W1p of Rn. Now you cannot approximate in L infinity norm by d of Rn. Because if you have functions with compact support, C infinity functions with compact support are in particular continuous functions with compact support, and the limit in L infinity norm would give you a function which vanishes at infinity. Therefore, u identically 1 does not vanish at infinity, it is 1 everywhere, and therefore you can never approximate this function by means of d of Rn, d of omega functions. So you cannot expect any of the results which we have proved for the infinity, so we have to exclude it. Okay, so now we will look at some applications of Friedrichs theorem which are very interesting. Okay.